Hello everybody, Claudio here. Today I'm gonna talk about how I have calculated the resistance of the frame of this press when it is in operation by the effect of the pressure exerted by this bottle, this jack bottle. And I'm not a mechanical engineer, so if I've made any error, please let me know in the comment section below. But I've tried to do my best to figure out how the forces are distributed along this frame, and to locate where are the critical points to calculate, to know if the press will be able to withstand the forces exerted by this jack bottle. So let's get started. Well, when this jack will expand by pumping with this lever, it will push down here and up here against this transverse and against this plane that lies on these two pins, and the force is the force exerted in these directions, here and here, along these two columns, and therefore the two critical points are here where there is the welding, and here where there are the pins. And in both cases we have a shear force, because here the pins tend to be sheared down, and here the force try to push up, and the column try to keep it in place, and therefore there is a shear force that try to snap out of the transverse from the column. And so those are the two critical points to calculate the press, because the columns are really much larger, and we don't care them. Shear force is a force that tries to move one part in one direction and the other part in the opposite direction. So imagine that the two parts are glued together. Which is the component that keep the two parts together? Well, it is the surface of the glue that keep the two parts, and that have to withstand to the forces, to the applied forces. Therefore, we have to use this area to calculate the ability of the structure to withstand to the applied forces. And while it's quite easy to calculate the pin, because it is just the section, the diameter of the pin, another whole story is to know which is the surface of the welding. So I'm gonna to make a sample to know which sides have the beds of the weldings. Well, this is a sample that I just welded to mimic this part here, this column with this part, and the transverse that is below here with this part. I will cut this part in this direction to see on this plane, to see through here how the weld it went, and in this direction, in this plane, to see through here, to see how this weld is went. However, because there is a problem here to hold the part on the vise of the saw, I have to weld a piece of scrap tube here to see to have. Wow. And now let's cut what? Okay, now let's cut here in this direction. Well, of course I will cut part of the tube, don't care. Well, this is the section cut, and we can see here clearly the junction here and here, and here the weldings here and here, and the size of the welding, roughly 4 millimeters here, approximately 3 millimeters here, and here we have 4. Let's check better. So the worst case is this welding that is only 3 millimeters in size and width. The width of this is just 3 millimeters, and this is the worst welding, the worst condition. Also, I've cut this part in two to see the section in this plane. 4. So in this case the weld went not very good here, but we have to keep in mind that the welding, it is not constant, and this point is just at the beginning and the corner, and on average the welding is distributed better along the line of weld, but here much better here. Of a size of a section of about 3 millimeters, that is on average a conservative number to take in account. So let's see how the forces are distributed around the frame. We have the forces up and down that are exerted by the jack, and the frame that resists to these forces, that is represented by the arrows around the frame. And these are the joints that are the critical points. In this upper corner we see one of the joints that is welded, and we see the forces that are in opposite direction, and therefore the joint is subject to a shearing force, and the purple shape it represents the welding, and here we see the surface of the welding of the bead where the force actually happens. And in this lower corner we see the pin that where the bar lies on, and it is represented in orange, and the forces that again are in opposite direction, and therefore the pin is subject to a shearing force. Now let's talk about the math. And with occasion, I have to say that in the previous video where I did show the making of the press, I've put a card with a load of typos. I'm sorry for that, but that is what happened when one do the things too late in the night instead of sleeping. The first thing to do is to look at the surface of the weldings, and keeping in mind that we have two seams, one that goes all around the external side and one that goes all around the internal side. And to do this, we can bring this part that is a profile that comes from the same kind of profile, and we can take the shape of the profile to have an idea where the weldings go, and measure the height. The height that is 37 millimeters. So let's write here the height 37, and the width that is 50 millimeters. All right, 50 millimeters, and the internal side is about 35 millimeters. So here and here are 35 millimeters, and from here are 35 again, 30, a little bit less. Let's see with this, and yes, it is a little bit less, so it is 32 millimeters. The inside is 32. Right, so here around we have a bead that is we consider it of just 3 millimeters. Actually, here we have something that is like so and like so. All right, the bead that goes all around. So we consider this width 3 millimeters as an average, as a worst condition, and therefore we have here an height of 35 millimeters and a width of 56 millimeters, and here instead we have a little bit less, so we can consider this maybe 3 millimeters less, 2 or 3 millimeters less, so say 28. And here we have 35 less, say 5 millimeters, 30 millimeters. All right, and in the lower corner we have the pins that are 15 millimeters, and we have to keep in mind that we have two sides, so we have a surface here and a surface here, in two sections that resist the pressure, the force that goes down. Well, I did a mistake. This is not 35. I've taken this number instead of this one, so it is 3 millimeters more than 37. Therefore, this is not 35, but it is 40. So let's do the math. We sum all the surfaces. We calculate the surfaces and we sum all together. So we have 56 times 3 millimeters times 3 millimeters plus 40 millimeters times 3 times 2, because we have 1 and 2 seams, plus 30 times 3 plus 28 times 3 times 2, which give us the best number of 666 square millimeters. Okay, now for the pin, we have a diameter of 15 millimeters, so we calculate this. By dividing the diameter by 2 to find the radius, square it and multiply by pi to get 354 square millimeters. And this, since we have the two sides, we have to multiply this by 2. So 354 times 2 gives us 708 square millimeters. And we see that, by contrast of what I've said in the previous video, in the video of making of the press, the weakest point is not the pins, is not in the pins, but the weakest point is the welding. So the weakest point of this press are these 2 pins. So we keep this number, this best number, as the weakest point for all calculations. So let's move on. We take this number, 666, and we multiply this square millimeters, and we multiply this times 240 megapascal, which is the strength of the material, and we get under 840 Newton, which is approximately equal to under 60 kilonewton. So let's take this number, under 59,840 Newton divided by 9.81 meter per square second, which is the gravitational acceleration, which give us 16,294 kilograms, which is approximately 16.3 tons, metric tons, of course. So let's take a margin of 30%, of the 30% margin, 16.3 tons times 30%, and we get the final value of 11.4 tons, which is the final number that our structure should withstand under force. However, that depends by the welding, and welding, if the welding are well made, okay, that could be a number that can be trusted, but well, you know, everybody know his ability of welding. Mine is not so good. If you look around on YouTube, you will find a lot of people that have made a press with a jack bottle. So I did mine. But at the same time, I also wondered Well, is the frame able to withstand the force exerted by the jack? Despite I'm not a mechanical engineer, I've tried to figure out a way to calculate, even though in a simple, crude way, just to have an idea if the frame is able to withstand the force applied. Because, you know, depending by the arrangement of the parts under pressure, if the frame fails under pressure, well, it could be quite dangerous. Okay, that's all, folks. I post videos on not on a regular pace, so if you are interested to follow my videos, consider to subscribe and click the bell icon. Otherwise, you won't be notified when a new video will be posted. Cheers from the Alps. Thanks for watching. See you next time. Bye.